giving floor to our speaker, Professor Dr. William. Sir, you can continue from now.
Oh, good morning or evening once again. And as Seifel has mentioned, I'll go ahead and share my screen here. We're going to apply the sedimentary structures to an actual field example today. So I think today's discussion will probably be a little bit more interesting. Okay, so this is part 2. Today we're going to briefly talk about facies and facies association, but the main thing is we're going to use these to interpret depositional environments and systems. I want to introduce you first to the area where we will be that we will be discussing. This region is known as the Book Cliffs in the state of Utah and the U.S. Let me go back a couple of pictures. The reason it's called the Book Cliffs is because to some it looks like a book that's laying on its side because of the horizontal strata. But what we're looking at here is a succession of interbedded mudstones and sandstones. And if you look at this picture at the top, there's a very thick, several hundred meters thick mudstone down at the bottom. Is called the Mancos Shale. And then the succession overall coarsens upward from the shale into a thick sandstone, but it's not uniform. At the bottom is a sandstone called the Panther tongue. You can see that there are a couple of smaller sandstones in here where the shoreline retreats a little bit, and then it advances once more. You can see that in the diagrams down at the bottom. Both of these diagrams show the same succession. One is a little bit simpler than the other. We're talking today about the interval that's right over here at the far left side of this diagram, and the area consists of sandstones that prograde into the basin and then are interfingered with mudstone from transgressions. So we're going back and forth between transgressions and regressions. The interval that we're working with is called the star Point-Blackhawk-Castlegate sequence. If we were talking about sequence stratigraphy, it's a single third order sequence. Excuse me? Oh, okay. It's a single third order sequence. But what we're going to focus on today is that each one of these dominant sandstones that you see has been interpreted as a deltaic deposit with interfingering with the marine shales. And so how do we use sedimentary structures to identify this as a delta? So rather than a river channel or an aeolian sand dune. Okay, this is a closer picture of the same succession. We're going to be, there's a canyon over on that you can see in the picture. We're in another canyon just like that one, and we're going to be walking up the one that's on that's behind my back as I'm taking the picture. But again, down at the bottom is the Mancos Shale. The Panther tongue is one of the units we're going to discuss, and then we're going to come up here. We're going to talk about the Spring Canyon member, and on another time, if you'd like, we could go through the sequence stratigraphy of the succession, but that's not the focus of today. All right, so first of all, just really briefly, the concept of a facies, because that's what we're working with here. A facies is basically a body of rock or a body of sediment that is that has a certain set of physical characteristics that are related to the environment in which it formed, to the physical, chemical, and biological conditions under which it was produced. But we're focusing on the physical aspects. A couple of examples on the left. This is actually that top sandstone we're going to talk about in a little bit, the Spring Canyon. ST stands for sand. Trough. This is a trough cross-bedded sandstone, and up above it is a horizontally laminated sandstone. There have been attempts, this is one on the right, that a lot of people are starting to use to informally use a shorthand. So rather than write out trough cross-bedded sandstone every time, we can simply write ST. Something that we're going to be particularly interested in here is the order in which these facies are stacked on top of one another in response to Walther's law. A facies association is where we have a group of facies that are genetically related. That is, they're part of the same depositional system. One of the a very common facies association that we talked about a little bit yesterday is the Boma sequence, an erosional base overlain by structureless sand, might be a little bit of gravel at the bottom, parallel laminated sand, ripple bedded sand, and then fine-grained deposits at the top. Okay, we see that pattern over and over and over again. It was formally described by Arnold Boma, so it's been named after him as the Boma sequence. Others don't have names, but are equally useful. This one, an erosional base, a lag gravel, a structureless gravel at the bottom, trough cross-bedded sand that becomes thinner bedded toward the top, planar cross-bedded sandstone, ripple-bedded sandstone, interbedded sandstones, and mudstones. This is a succession that we often associate with meandering river systems. On the right is another example where there are mudstones interbedded with hummocky sandstones. The sandstone becomes more dominant upward, giving way to trough cross-bedded sandstone, parallel laminated sandstone, and then there can be a variety of things up at the top, and that's become associated with the beach. But it's that vertical stacking of facies that allows us to make that interpretation. And the facies are stacked because of Walter's law, which very simply states that in a vertical succession that is not broken by an unconformity, the facies represent environments that at one time were adjacent to one another. Okay, so let's go ahead and apply this now to this area in the book cliffs. Okay, I'm going to start down here at the bottom. Okay, we're going to focus mostly on the Panther tongue, but beneath the Panther is this unit that's called the Mancos Shale. The Mancos Shale is primarily composed of clay with little silty interbeds. And the further down we could go, this unit right here is probably about 300 meters thick, the Mancos Shale. And if we drill the holes through here, we'd see that down toward the bottom it becomes more and more clay rich. Toward the top, we start to see some silty interbeds. The silty interbeds increase upward. Eventually, across the boundary, they start to become hummocky sands. The silty beds can have a weak rippling associated with them. So this is a unit that had to have been deposited primarily under conditions of suspension, of sediment suspension and settling, and that's going to form the mud. But occasionally there's an event that brings a little bit of silt out here, and there's some traction deposition as well. So looking at this diagram on the left is the dark green material that's down here at the very bottom of the diagram. Okay, the Panther tongue. This is where our facies, our sedimentary structures, are going to, so a sedimentary facies in most cases is going to consist of a grain size and a sedimentary structure, such as trough cross-bedded sand. So the Panther tongue member is the sandstone in this diagram that's extending a little bit further out into the basin, and the dominant sandstone that you can see at the bottom of the ledge. You can notice above there are some other weak sandstones. These are the ones that are backstepping in this area. Okay, now the Panther, looking at it, I just wanted you to look at it for a second, and can you identify any obvious changes in the depositional pattern through this succession of rock? As I've studied this, I tend to divide this unit into three, or this member into three informal units. Down at the bottom is a unit that consists of interbedded sandstone and mudstone. And then up above it, here's a sandstone. The way that it's weathering is a little bit more blocky than what's up above. And so I put another boundary up through here, and I've had that drawn here in a moment. And then the upper part is a sandstone that's a little bit more rounded. Each one of these consists of a different set of facies that can be used to identify the environment in which it was formed. But I want you to notice the overall pattern before I move out of this picture, that we're going from interbedded sandstone and mudstone to sandstone with just a little bit of mudstone, and as we get toward the top, it's almost entirely sandstone. Okay, so the basal unit, this part that's right here down at the bottom, I've got a number of photographs that are pointing to some beds that are in there where I found a number of sedimentary structures. What we're looking at again is interbedded sandstone and mudstone. Now in this case, I want you to think about the facies associations that we've discussed. These sandstone beds tend to, at the bottom, have an abundance of flute casts. I didn't talk about those yesterday. Flute casts are erosional features that are produced by fluid flow. It's almost like taking a garden hose and spraying the surface and watching the erosion. And then they become filled by the sediment up above. The next picture over, tool marks. These are features that are formed as a stick or a clay clast or a shell, or some feature is drug across the surface, gouging it and creating a groove that is later then filled by sediment. So the bottoms of these sandstones are erosional in nature and contain an abundance of these features, these flute casts and tool marks. We also see load casts. That's simply because of the sand that is overlying the clay and it's compressed down into the clay. The sandstones themselves, if we look at this other photograph here, hopefully you can see my cursor. I haven't been able to change it for these presentations. But these sandstones, I showed this picture to you yesterday, erosional base, and these are what we'll see on the bottom, the flutes and the tool marks. Structureless sand, parallel laminated sand, ripple bedded sand, then here's the mud that's back on top. You know, that should look familiar from our discussion yesterday and from a couple of slides ago when I was talking about the Boma succession. Again, and then the ripple bed of sand, this is another one of these Boma successions. On this one, you can clearly see from the orientation that these are climbing ripples. Okay, so these are high energy events. Some other things that we will see in here that I didn't include in the pictures, an abundance of burrowing, ophiomorpha burrows, scalithos burrows that start at the top of the sands and can go all the way through them. Okay, so to have formed this interval right here, and we'll keep this in mind for a little bit, we need to have a setting in which the water at times is quiet enough to allow the clay to settle out, and at other times the energy is high enough to deposit these sandstones that go from, essentially upper flow regime and drop down through the lower flow regime. And so high energy with decreasing energy during the time of the flow. Okay, moving up into the middle unit. The middle unit is much more uniform. Notice that there's a little bit of mud in here, but not a lot. It's primarily sandstone. These sandstones in the middle unit, you can see it in the upper right photo, are a lot like the sandstones that are in the bottom unit, except they tend to not have the upper part of this ripple. They tend to go back and forth. Right here you can see a structureless sand and a parallel laminated sand up above it. And so we have these couplets of structureless and parallel laminated sand. And so in this case, we need to have an environment that is still allowing these same types of high energy deposits to accumulate, but is not allowing the mud to be deposited, or at least to be deposited and to be preserved. So in this case, we're looking at Boma sequences, but they're not complete. They're missing the upper part, and this is very common when you look at a turbidite. The turbidite near the source is going to be dominated by the basal parts, the erosional bottom, the structureless, and the parallel laminated sandstone because of the high energy, and then the upper material continues to move down the slope, down toward the toe of the turbidite. You're more likely to see the ripple bedded sand and the siltstone that's up above does not have the bottom part, and in the middle of the turbidite you tend to see the whole thing. So what we're seeing here is we're going from what look like distal turbidites into more proximal turbidites. Okay, and then the upper part, okay, well, there's a significant change across this boundary. Once we move across this boundary, we no longer see the Boma successions. We do see parallel laminations. You can see that in this figure close to the right. But we also see trough cross bedding. You can see some troughs in the far right photo. Much of the sand appears to be structureless. And then there are intervals. You can see one right up here, and there's another one over down a little bit further that is made up of interbedded sandstones and mudstones. They tend to coarsen upward. There's a big difference in the mudstone here. Rather than being a bioturbated mudstone such as in the lower part of the succession, these muds are essentially structureless and can be rich in organic material, basically small coal fragments. And then the upper surface of this and the upper surface of many of these sand beds is highly bioturbated. Okay, now what we're looking at, and another thing that I should mention here is that these beds, if you follow these beds, this one here, it pinches out just a little bit outside of this picture. This bed pinches out right up through here, and it becomes thicker to the right. The beds in this upper part are more lenticular, they're discontinuous. And so you have an interval of sands with a variety of sedimentary structures that are interbedded with thin, organic-rich mudstones. And so again, we're looking at a situation where we're probably more landward than we were in the one that's underneath. Okay, so in terms of interpretation, so how have we used the sedimentary structures to identify the depositional system? First of all, what is the system? Okay, now if I were in a classroom with you in front of me, I'd probably ask you questions and have you come up with the answer, but being remote, I'm just going to go ahead and explain it. The Panther tongue member has been interpreted as a river-dominated delta, and the basis for that is the structures that form the facies and the way that they change in a vertical succession. So we're using Walther's law. If I look at this lower right diagram, this picture is from a lake here in Idaho where there's a river that is forming a delta and mud is being transported out into the basin. So out here in the basin would be the equivalent of the Mancos Shale where the mud settles. And then as I get closer to the edge of the delta, during storm events, I'm likely to have sand that extends a little bit further out into the basin that will become interbedded with the mud. And moving a little bit more inland, it becomes sand dominated. And then toward the top, the beds are lenticular because of the fluvial processes. So what we're looking at is a situation where down at the bottom, we have structures that indicate that we had alternating episodes of high energy and low energy. Okay, the diagram in the lower left, the inclined black line represents the beach face or the shore face. And the blue lines represent essentially features that are controlling energy levels. Base level, sea level is an obvious one of those. Where do we have breaking onto the beach? We have it where right at sea level, where the shoreline is located, where the sea comes into contact with the land. Okay, and waves, wave energy decreases with depth, but at some point that wave energy comes into contact with the shoreline, and when it does so, it's going to have a winnowing effect. So down here at the bottom, the waves are probably very weak. They're weak enough to prevent the mud from settling, but probably not transport sand along the beach. A little bit higher in the succession, the waves are going to be strong enough that they actually move sand through longshore transport. Another important energy elevation is storm wave base, where if there is a larger storm, then that wave energy is expended down to a greater depth. but that's only periodically. And it's in this area where we get the quiet episodes during fair weather of mud being deposited, and then a storm sand, and then mud, and then a storm sand. Now in this case, instead of storm sands, we're looking at sands that are deposited off a delta front in the form of turbidites. So think of a river mouth. Look at this one over here. If this were a much larger river, such as the Mississippi or the Nile, or one of the many others, that during the spring, when the runoff is high, sediment will accumulate. It will stack to the angle of repose at the mouth of the delta, and then it's going to fail and move down the slope in the form of turbidites. And that's what we're looking at in this case. But that's going to be what we see down here in what's called the transition zone. Now in this case, instead of a regular shore face, what we're looking at is, based on the sedimentary structures, channel mouth bars. When a river enters a standing body of water, such as the ocean or a lake, the sediment load that it is carrying, the bed load, is going to be deposited very rapidly. And remember that one of the things that we talked about that might lead to structureless sand bodies is very rapid deposition. Deposition is fast enough that the sediment doesn't have time to be reworked by other processes. And that's where we get some of the, going back to this picture, that's where we get some of the structureless sandstone beds. But this sand, once it's deposited at the river mouth, is then going to be reworked by marine processes. So much of this structureless sand is going to be reworked by waves into parallel laminated and trough cross-bedded sandstone, depending upon the depth. And when the river avulses and changes and starts building a new delta lobe, and the old delta lobe is abandoned, that's going to allow the lobe to subside, to be covered with water, and that's what's going to provide us with these finer grained intervals, such as this one right here, where we have a carbonaceous mudstone, a mudstone that has a great deal of carbon, of coal that's associated with it. And another thing that we will see in between these interbedded sandstones and mudstones are likely the splays that are developing off the margins of the primary channels as the channel is creviced. And so hopefully, what we've been able to demonstrate here is that by looking at the sedimentary structures that we discussed yesterday, and the association they have, that is the vertical accumulation, as the lower part of the delta prograded over the marine shelf, and then the upper part of the delta prograded over the lower part of the delta through Walther's law, that these facies are stacked on top of one another. Okay, so that's an example of a river-dominated delta. Now, I'm not going to talk about this area right here in as much detail. The previous picture, this one was taken about 5 kilometers away from this photo, and this is the same unit. This is also the Panther tongue member. So if you look at the right, that's very similar to what I just showed to you in the last photo. But then continue moving leftward, and notice that those channel mouth bars have been incised, and they've been filled with another sandstone. And we've interpreted this sandstone as a distributary channel. And just really quickly down at the bottom, okay, again, you can see the channel morphology on this lower picture. But some of the things that we see in here that are different, even though it's the same formation, a lot more trough cross bedding. There's still some horizontal laminations, but some other things that we see at the bottom of some of these channel forms are clay clasts that have been ripped up. There are a lot of small channels that are within the big channels. Within the channels, there are mudstone interbeds. We talked about wavy and lenticular bedding yesterday. So here we're going from, this is almost flagure at the bottom, becoming more lenticular toward the top. Double make clay drapes, which is indicative of tides. There's a little bit of flagure bedding, and right here. This one has another trace fossil. It's a little bit hard to see in this photo. It's right in the middle, called Teridolites, which is also indicative of tidal influence. So here we interpret this as again, based on the sedimentary structures and their association, as a distributary channel within this deltaic succession. So this is the delta front, and here's a distributary channel that cuts across the delta front, and it exhibits tidal influence. And just to give the full picture, if you go more basinward instead of more landward, this again is the same unit that we're talking about. This is the Panther tongue once again, but a little bit further out into the basin. And so, what has happened to all of the sand? As you move basinward and you move into deeper water, the sand is not able to be transported that distance. We still have the vertical accumulation of sediment, and so the Panther tongue eventually starts to look like, and actually a little bit further, just becomes another part of the Mancos Shale. But you can still see some of those cycles that are within here. And so this is one of the reasons I wanted to talk about the Mancos before, is so that you can see the relationship. And so what you're looking at with those pictures, the distributary channel is back over here. The pictures that I was showing to you of the delta front is right there. This is the delta front in this area. And as we move to the right, the picture down at the bottom, this is the distal part of the delta. And so over this short distance, now this is a diagonal picture. So in about 1.5 kilometers of down dip direction, you go from the distributary channels to the fine-grained deposits. And this is an important concept if you're involved in aquifers or in petroleum reservoirs where the continuity of the sand beds is significant. And so to just wrap this up, a modern analog for the Panther tongue is this delta right here, actually both of these deltas. These are the Wax Lake on the left and the Atchafalaya deltas in the state of Louisiana. This is the Gulf Coast. And if we take the Atchafalaya, the picture with the distributary channel would probably fall about there. The one with the delta front sandstones about here. And notice how quickly we become the very muddy unit. And so in a very short distance, you have those changes in facies. So the sedimentary structures are different in each one of those three, and the sedimentary structures are what we can use then to determine, in this case, is one of the things that we can use to determine the direction of sediment transport, from land to the basin. Okay, so hopefully that made sense to you. Okay, we're going to now jump up the section. If we're talking about sequence stratigraphy, I'd go through all the stuff that's in here as well. But we talked about the sandstone, which is the one down at the bottom. Now we're going to jump all the way up to the sandstone that's at the top of this pile right here, or almost at the top. And it's actually this little bed that's right here where the arrow is pointing. And so what we see is we've had a major transgression where we go back into a significant amount of mud. And now we're starting to see a regression once again, and these are some beach sandstones. Okay, the succession that we're going to look at up above is the one that's on the right. This one is known as the Spring Canyon member of the Blackhawk Formation. Okay, and once again, we can divide this into a number of units. In this case, I've broken it up into five separate units. The one down at the bottom is interbedded sandstone and mudstone. The one in the I'm sorry, this is a different unit down here. Right here, this is the interbedded sandstone and mudstone. That looks a lot like the base of the Panther tongue. And then this is an amalgamated sandstone that from here looks a lot like the next unit in the Panther tongue, but then it becomes quite different. This is a thick interval of trough cross-bedded sandstone and a thick interval of parallel laminated sandstone. So let's talk about each one of these individually. So we'll talk about the basal unit here first. Okay, so as I mentioned, it's interbedded sandstone and mudstone, but I want you to notice that the sandstone in this one is very different. Oops. Whereas in the Panther tongue, the sandstone consisted of a Boma succession. Notice that in this case, the dominant sedimentary structure is hummocky bedding. So hopefully you can see the curve that's associated with this deposit. So in this case, the sandstones were not deposited by turbidity flows. In this case, the sandstones were deposited by storm events. And so it's they're significantly different in the internal structures from those that we saw before. So overall, standing back, this unit and the Panther look very much like one another. And if I didn't go up to them and look at them closely, I might interpret them as having formed in the same way. But when you go up and you look at the details, primarily the structures, you can see that there is a significant difference between them. But like the Panther, we go from, okay, the red is the bottom of the unit. The stuff under the red I'm not talking about. So we go from interbedded sandstone and mudstone to predominantly sandstone with a little bit of mudstone to almost just sandstone. So once again, we're seeing an overall coarsening upward and shallowing upward succession. Okay, let's move up one to the second unit. The second unit consists of the same kind of sandstones as underneath, but without the mud. So once again, we're looking at hummocky stratification, but in this case, the hummocks are stacked on top of one another without mud in between. So here's a hummock, there's another hummock, there's another hummock that's on that's on top. So as with the Panther tongue, we've gone from a situation where we have a setting where the energy is low enough to allow the accumulation of mud, and then it's punctuated by very high energy events, to only the high energy events are preserved. Okay, we move up a little bit further into unit 3. No. Have I missed one there? Oh, there we go. Into the third unit. Okay, that arrow should go up a little bit higher. Sorry about that. And now we're looking at a situation where we see a lot of trough cross-bedding. So this entire ledge up here near the top consists of trough cross-bedded sandstone. And the trough cross-beds have a variety of orientations. You can see that here. This upper trough looks like it's going into or out of the slide. This trough here looks like it's going to the left. In reality, they're all going into the slide, but at different angles. So there is a significant range in the directions of the paleo currents. And am I missing a slide? Oh, I am. Okay, I'm missing one of the slides. I want you to, in the upper right here, notice the parallel laminations. Or here, let me go back. Okay, so this would be unit 3, the trough cross-bedded sandstone. Can you see that sharp boundary? And up above is the horizontal laminated sandstone, and that's this is unit 4 of the figure that we're talking about here, the Spring Canyon. When I send these slides out to people, I will make these corrections first. Okay. So the trough cross beds, as we talked about yesterday, are formed under conditions of lower flow regime, and as the energy increases, then the trough cross beds tend to become a little bit larger, and we do see that in this outcrop. That at the bottom, the troughs are a little bit smaller than they are at the top, and across this boundary, we make a transition. If you can think of that last picture I just showed, this whole unit up here, number 4, consists of parallel laminated sandstone. And so we've crossed a boundary from lower flow regime into upper flow regime that's producing that sedimentary structure. And then finally, at the very top is coal. There's a very thin coal bed that runs all along the top of this, this ledge. And that's a regional coal bed. It goes for many kilometers in all directions from this location. Okay, so the coal clearly represents that we have transitioned from the marine into the shoreline and up here into terrestrial conditions. So more like a swamp where there's a significant amount of plant material that's accumulating to produce the coal. Okay, so putting the whole thing together in this case, I showed you this diagram in the middle a little bit earlier, where we talked about marine mudstone that is interbedded with hummocky sandstone, and then the hummocky sandstone gives way to trough cross bedding, parallel laminations, and then there can be a variety of things on top. In this case, it's coal. So those pictures that I've shown to you before, they're all here again, and you can see them in succession. So what I want to get across with this figure here, with this slide, is this, again, this idea of using sedimentary structures in a vertical succession to identify the depositional system. So as we look at this, there are some boundaries that are present here once again. So here's the same diagram that I showed to you before. Underneath, in the trees down here, there's some marine shale. There's a tongue of the Mancos Shale. Okay, and then there's another thin interval that's right at the top, about where that red line is, but it's very, very thin. Then right here in this interval, in zone 1, that's the transition zone, where we get, during fair weather conditions, deposition of mud; during storm conditions, deposition of the hummocky sandstone. Then we cross the storm wave, the fair weather wave-based boundary into Unit 2, and in Unit 2 we're still seeing the hummocky bedded sandstones, the storm beds, but they lack the mud. So here the wave energy is strong enough that it is preventing the mud from being deposited, but it's not strong enough yet to move the sand. Moving up the shore face, up in this area right here, we move into zone 3. And in zone 3, the waves are now strong enough that they can move sand along the shoreline. They're producing small waves and dunes along the coast that are resulting in the trough cross stratification. The reason that there's a variability in the trough direction is that the wind doesn't always blow in the same direction. And then this next boundary at base level, where the waves are crashing onto the beach, that's Unit 4, where we see the parallel laminations. And then at the top of the succession in the back shore is where the coal is accumulating. And then using Walther's law once again, the sediment can only accumulate up to approximately base level. So often in our introductory classes, we indicate the base level is the level to which continents can erode. It's also the level to which sediment can accumulate in a marine setting. And so once the sediment accumulates up to base level, then the beach progrades into the basin, and this is how we stack these various facies on top of one another. So we go from the interbedded sandstone and mudstone to the hummocky sandstone, the trough sandstone, and the parallel laminated sandstone. They become stacked on top of one another because of Walther's law through lateral migration. Okay, so this succession has been identified by many as reflecting a progradational beach. And where you're likely to get a progradational beach is going to be close to a river that's carrying a lot of sand in a zone that has high wave energy. And so these are also reflective of wave-dominated deltas. Okay. So again, notice that what we've done here is we've taken the facies. We have two different outcrops that from a distance look like one another, but we've been able to come up with different interpretations of their depositional system based on the sedimentary structures that are present and the order in which they occur. So the facies association. So one of the primary things that I do when I'm in the field, or if I'm looking at a core, is I'm identifying facies and I'm looking at the order in which they occur, so that I'm allowed to then make an interpretation of what the depositional environments and system might be. And where another place where this becomes very useful is then, you know, across 5, just really quickly to go back a couple of pictures, notice that on top of the coal, here is another sandstone that looks like the ones that were down below. So this is going to represent a rise in sea level, and we have a whole new beach succession that's prograding into the basin. Okay. Okay, as I did with the Panther tongue, I just want to show you what this unit looks like as we move further landward and basinward. It's the sandstone that's right here at the top. Okay, and if you look really carefully, hopefully you can see my cursor okay. As you move from right to left, so here's the top of the sandstone, it ends right there. And so this would be the barrier island that's on the landward side of the prograding beach. So when base level rises, a barrier island is produced. When base level stops rising, then a beach forms off of that and progrades out into the basin. And then this area behind it right here is very different from what we're just looking at. So these pictures on the right are of the interval that's right behind the barrier island in the lagoon. So these are also part of the Spring Canyon member, but notice that they look quite a bit different. Some thinly interbedded sandstones and mudstones. This might be a bayhead delta or a splay. They're climbing ripples. There's right here indication of tidal influence with some of the flasier bedding. So a number of sedimentary structures. Again, I won't dwell on that one. Unfortunately, I couldn't find, when I was looking last night, a picture of the more basinward expression, but the more basinward expression looks just like the more basinward expression of the Panther tongue. All of these units in a basinward direction eventually become the Mancos Shale. As they pinch out, they become more muddy. A modern analog for this one is the Sao Francisco Delta in South America. And notice that what we have here are a bunch of beach ridges. So the river comes through, and we do sometimes find the distributary channels for these as well. As the river enters the sea, it drops the sand, and then the sand is reworked away from the river mouth by longshore currents to form a beach that progrades out into the basin. And on the left, there's a barrier island with some of the lagoonal facies that are present behind it, similar to what I showed in that last photograph. This one on the lower right, I don't know where this picture was taken. I think it was the U.S. Atlantic coast. But again, you can see that the sand can only build up to sea level. And once it builds to sea level, then the only place for the sand to go is to accumulate in a basinward direction. So each one of these lines here, each one of these ridges represents a basinward migration of the beach. And so if I were able to dig a trench here or to take a core right here, I would probably see a succession of facies that is very much like that I just showed for the Spring Canyon member of the Blackhawk Formation. Okay, so to go back to where we started on this, we looked at, here's the Panther tongue, and then this is the sandstone. This is the Spring Canyon member that we looked at. The pictures down below, the beach progrades into the basin, and then there's a transgression. The beach progrades into the basin, and there's a transgression, and we see this, or I should say, the delta, and we see this over and over and over again through this interval. And but this down here, this delta, notice it looks a little bit different now from this perspective than the one that's up above, and dominated by river processes, dominated by wave processes, and that actually is the extent of. I thought it would take me a little bit longer to get through that. I'm happy to go ahead and discuss further or add other figures in here if you'd like. or we can go ahead and open it up to questions. So, Saiful, what's your thought?
Okay, sir. Okay, we are heading for the question and answer session now. If you have any question, you can actually drop your question in the chat box. Sir, can you? Would you like to extend your presentation now, or this is our end presentation?
What's that? Well, this is the end of what I formally prepared, okay. But I can discuss more if you would like. I could talk about some of the stratigraphic effects that are over here to the left. Normally, when I give these presentations, I have a group in front of me, and I'm asking questions, and they're giving responses. So I wasn't quite sure how long this would take me, and I went faster than I thought I would. But I can talk a little bit more about the sequence stratigraphy over here if you would like.
Yes, sir. I think you can actually go ahead, sir. Please, sir, go ahead. Go ahead.
Okay. Okay. So on this figure, on the right side, I have the lithostratigraphic units. So the Mancos Shale, this is the Panther tongue. Here's the Blackhawk formation and so forth that I've already talked about. Now on the left, I've got some other indications. Oops. I keep accidentally moving the mouse. Okay, SB stands for sequence boundary, TS for transgressive surface, and MS for maximum flooding surface. Let me bring up another set of slides to show what that refers to. And so, just in case I ended early, I've got another presentation here that I gave to SDA at one point. Now, for some of the undergrads, this diagram might be a bit confusing. I would imagine that the graduate students in sedimentology are going to understand what we're looking at right here. But we're looking at a sequence stratigraphic model, and what we're looking at in this case is how these deltas are prograding. Think of that diagram that I had at the bottom of some of those pictures where it showed the sandstones that were migrating out into the basin. Each one of these little bumps here would represent something such as one of those sandstones. And when we're dealing with sequence stratigraphy, what we're looking at is a cycle of sea level change. So sea level drops, there's erosion in the landward area that forms the unconformity that you see in the red, and there's deposition more basinward. Then when sea level starts to rise, well, what that does is it allows these deltas to prograde farther out into the basin. And then as base level starts to rise, the deltas start to form this pattern of these tongues that interfinger with the mudstone. When the base level rises even faster, then you get that backstepping pattern. We saw that in the stores. And then the spring canyon was up here. So this is the Panther tongue. This is that muddy interval in the middle of the stores. Then up at the top was the spring canyon, where we move back into a progradational type of a pattern as the rate of sea level rise slows down. And there's certain surfaces in here that represent the sequence boundary, a drop in base level. The transgressive surface is where sea level starts to rise faster than sediment arrives to the basin. And then the maximum flooding surface is where the sediment supply starts to become greater than the rate of sea level rise, of space production. So back to this diagram right here that I showed before. So here's the Mancos Shale. So if you're thinking of that, if you think about that diagram with the little half circles that I just showed, okay, here's that red line. And then as base level dropped, we have what we sometimes call the falling stage systems tract or the Lowstand systems tract, which prograded, this one down here at the bottom right, prograded a significant amount, a significant distance out into the basin. In this picture, notice that up above it, there's a weaker sandstone, and then a weaker sandstone yet, and one that's really hard to see. Way back in there, you can see it a little bit. There's another even weaker sandstone. And so what we're seeing is that each one of these is less well developed than the one that's underneath. And what that is telling us is that the deltas are forming, but they're not making us far into the basin. And so back to our discussion on sedimentary structures, the way that I would identify that is in the Panther, we go from the transition zone all the way up into the shoreline deposits, or in this case, the channel mouth bars. And then this next one up here, I can show you some pictures. All that we see in this one is we're back in the marine shale. Then we have a transition zone and just a little bit of lower shore face. And then this one, pretty much just the transition zone. The next one, almost none of that. And so what we're looking at is deltas that are further and further away rather than closer and closer. So this backstepping interval that I'm circling down here in the lower right hand or the lower left hand figure. Okay, so I'll just go through and show those really quickly. So you might recognize some of these pictures. This is where I took a lot of them from. This is another presentation that I gave. We've already talked about the Panther. There's a lot more that I could say about it. Okay, but up above it is the stores. So down at the bottom, here's the Panther tongue, which we've looked at in a lot of detail. And here's a closer picture. Then the Mancos transgresses again. And notice that up above in this one, you can see that there's the interbedded hummocky sandstone and mudstone. And then here's the hummocky sandstone stacked. But notice that we don't have anything above that. There's no trough, and there's no parallel lamination. And another what we call a flooding surface. So the Mancos Shale comes in once again. And then we go up to this next interval right here, and it's even less well developed. It's mostly just some of the transition zone, and then there's another one that's right up through here. And so hopefully you can kind of see that what's happening is what's in this lower diagram on the left. The delta prograded into the basin, base level rose. The delta did not prograde as far into the basin, and then the delta rose, or the sea level rose, and the delta didn't prograde as far into the basin. And so we have a backstepping pattern, such as what you see in the lower right-hand part of this diagram. And so that one that looks kind of like a clam, we have the drop in base level, deposition of the Panther tongue, and with the green, can you see the backstepping pattern that's similar to what we have in the diagram down here? And this is what it would look like in Outcrop. Okay, so this is just looking at them up closely. So this next picture, where here it says KSSP1, that's the stores member of the Star Point sandstone. So this next picture is right here. So the next three pictures I show are going to be here, here, and up there. And hopefully you can see that this one looks a lot like the beach that we saw before, but it doesn't have a top to it. All it has is transition zone. That's not sand, that's mud. And so it has a transition zone, and then we get into the lower shore face. And the next one up, transition zone, and that's all. There's no lower shore face. And okay, and then there's actually one up above that I didn't put a picture in. So this is that same interval down there. The Panther tongue is down in the out of the picture, and these are the two sandstones that I just showed. And then the Spring Canyon that we looked at earlier is right up through here. Now I'm going through this really fast, quickly, so hopefully it's making sense. Okay, just another picture of the same thing. Panther at the bottom. Notice that these stores pair sequences become progressively less well developed, and then it turns around and we go from progradation in the what we call the Lowstand systems tract to retrogradation in the transgressive systems tract, and up through here, and then it turns back into progradation in the high stand systems tract. Okay, and so the Spring Canyon member, which I showed to you before, is going to be in this upper part. Okay, and that's this unit right here that's got the white cap. There's the coal that I was talking about a little bit earlier. A lot of times you can identify coals by this white discoloration in the sandstones because the organic acids that have migrated through and have altered some of the feldspars and removed them. Okay, so in this case we have just the opposite. This succession is not as well developed as the next, and then the one after that is even better developed and even better developed. And so we have just the reverse characteristic that's taking place here, that each one of these prograding deltas is better developed and more complete than the one before, until we start preserving only the tops rather than the bottoms. Okay, and so then we go through the various parts of this sequence right here, which I've already shown to you. So there's the bottom of it. So if I go back a couple, that succession right there, there's the bottom, and there's the top. Okay, and these other things I've already kind of showed you. Just one other thing, if we go a little bit further, right here is the top of that shoreline sandstone, and everything above that is fluvial, coastal plain. So this is fluvial, and this is braided river, and so that's simply, and this is a close-up of the lower and the upper parts of that picture, and that simply shows that the prograding has continued. So we go from the marine deposits to the beach deposits to the coastal plain deposits to a braided river system. Okay, and so I just went through an hour-long discussion right there in about 10 minutes, and hopefully that made some sense. Was that useful to hear that discussion about base level?
Hello.
So okay. All right. Well, and why don't we go ahead and go into the questions from here? Without getting into a lot more detail on sequence stratigraphy, that's about as much as I can cover on that.
Okay. Thank you very much, sir, for your this mesmerizing presentation again. I would like to ask the audience that if you have any question during about the sessions, please raise your hand to ask the question directly to sir, or you can also ask your question in the chat box.
Okay, I think there's a question from Junaid Khan Shejan. He asked, I was wondering, in the sedimentary sequence modeling that you showed us, does the backing process occurs with sea level rise? The green line, he says.
Okay, I'm sorry. You kind of cut out there for a minute. You're asking about this one here, the maximum flooding surface.
I'm just going to repeat the question. Is that okay?
Yes.
I was wondering, in the sedimentary sequence modeling that you showed us, does the backstepping process occurs with sea level rise? The green line maybe.
Yes, let me.
So he's mainly indicating in the MFS line that you are showing now. The slide.
Okay.
In the slide.
Let me move this out of the way and go back into. Okay, so yeah, I'll slow down a little bit on that now. So with this pattern, let's look at the box in the lower right here. Oh, I keep in the lower right. Okay, notice that the sand extends far out into the basin, and then it backsteps through here, and then it extends out into the basin again. What we're looking at is a balance between the rate at which sea level rises and the rate at which sediment comes into the basin. Now, through this entire succession, base level is rising, except for the very bottom. Base level drops and forms this one, but through the whole rest of the succession, other than some small drops, base level is overall rising. But what's happening through this interval is that base level is rising faster than the sediment is entering the basin. And then sediment is entering the basin faster than the space is produced. And so we have a couple of other surfaces right here, what we call the transgressive surface and the maximum flooding surface. The sequence boundary represents the drop in base level. Transgressive surface represents where the backstepping pattern starts, where the shoreline starts to migrate landward. And the green one, the maximum flooding surface, represents where the shoreline stops moving landward and starts to regress, move basinward once again. And so these bracket the backstepping pattern. This is the bottom of the backstepping pattern. That's the top of the backstepping pattern. Did that answer the question? So if we look at, I can find this diagram right here. So here is the prograding forming the Panther tongue. And then the blue is the start of that backstepping pattern, what we call the transgressive systems tract. And then this darker green line on top is where the shoreline starts to migrate basinward once again. And so those two lines are going to bracket, they're going to enclose the retrogradational part of the sequence.
Okay, I hope that the answer was actually recurring to the questions hour. Is there any other questions from the audience?
Oh. That's the fewest number of questions I've ever had.
Okay, I think there are no other questions coming from the audience.
Okay.
Maybe. Okay, so I would like to ask Turjo to share a contribution screen. We will now proceeding to the contribution session. Hello, Turjo, can you hear me?
Yes.
Yes, Subhabhai, I'm hearing you and I'm sharing it to you.
Okay. 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 Thank you everyone for this beautiful our UDGS outreach program. I would like to thank our Vice President Tasnim Barsinim to coordinate the communication with several participants. I mean, there are a couple of numbers who are actually the couple of executives in our UDGS, so who actually successfully accomplished this our event. The event's technical part and emailing part was successfully done by Daniel, who is our Secretary of UDGS. I would like to ask Turjo to slide the presentation just to show the certificate of appreciation. Okay. The overwhelming response of the registration was very technically handled by Nasif Jamil, Treasurer of UDGS. Our intellectual organization secretary, Muhammad Sulaiman, hosts the sessions and prepares some quiz sessions from the sessions. The most praiseworthy work has been done by membership chairperson of UDGS, Jayed Abdurrazak Turjo. He successfully handled the technical difficulties as well as the outline of the quiz patterns. He is also an enthusiastic designer. The event cover was actually done by him. Publication Secretary Nubahu Suba Chaudhary is working on the certification and quiz questions. Johur Ahmed is a very enthusiastic character in our UDGS space. He is the Officer and Logistics Secretary of UDGS. He resembled the outreach of the event in the several geological departments across the country. And our youngster Naushad is the newcomer in UDGS. His representative work benefited the event in the many forms. And most importantly, our heartfelt gratitude to Professor Dr. William for giving us his precious time to conduct this event. Thank you, sir, for your so supportive presentation and your overall in very important time to share with us. And hello.
Oh, just thank you very much for inviting me, and I hope that I gave you something worthwhile.
Yes, sir. You have that actually about we have given our.
Hello.
Hello.
Can I ask? Can I tell
Yes.
2 words?
Yes. Sure.
So I am Lubna Telsas from Morocco. I would like first of all to thank you for the organization and also for allowing to my students to be part of these presentations today and yesterday. And I would like also to thank Professor Little for this wonderful and very interesting presentations. Yesterday, I had a very good appreciation from my students that they appreciate the presentations. We already saw the most of the structures during the course, but in fact your presentations there were a lot of videos and also modeling which shows the structures, how they form. So they really appreciate and they really learn a lot about from that. And of course during this year we couldn't do the field trip as most of you we couldn't go outside. So this presentation of today was very good because at least we could see the structures and also see how we can, or how it could help us to know the depositional environment. So thank you very much, Professor Little, for this very interesting presentation. Thank you very much for University of Dhaka for this, for inviting us and giving us this opportunity to also be part of this and to know more about sedimentology and geology. Thank you very much.
Thank you.
Okay, thank you. We are also very pleased to having you. Yes, I hope you have learned. You and your students actually learned a lot of things from the sessions. I think. Yes, and thank you very much for joining us. Okay, now a quiz session will be held, and now the participation of the quiz will be received a verification certification from UDGS. And please don't worry about the scores because there are just some basic questions to evaluate just your participation, and your scores won't be shared. So just participate in the quiz. And I would like to ask to Joe to share the link in the chat description.
Yes, Oppo bhai, I have already shared that.
Okay. Please everyone follow a link in the chat description to participate in the quiz. Please remember the quiz time is 15 minutes, and after 15 minutes the quiz the doc will be automatically closed. So try to submit before 15 minutes. Request everyone to just open your video so that we can actually capture a screenshot of the session. Thank you. Surjo, are you ready to take the screenshot?
Yes, bhai, I am taking the screenshots.
Okay.
Okay, 3, 2, 1. Yes, I am done. Thank you.
Okay. Okay. Thank you, everyone. Thank you, sir, again. And hopefully everyone will get your participant certification based on the quiz participants. And hopefully everyone will be doing well in this pandemic time. I wish everyone a very good luck in your upcoming days. Thank you, everyone, and thank you, sir, again.
And we would like to thank
before ending, I would like to thank Oppo Bhai. Without
We would like to thank our president, Saiful Islam Opu, for arranging this program so nicely. And thank you all of you for participating in this program. Wish you all the best. Stay home and stay safe. Good luck, everyone. Thank you.
Thank you so much.
Thank you.
Thank you.